Great. So welcome everybody to our first review meeting for 2026. Today we actually have a special edition for the Kubernetes 1.34 release. So we follow the usual agenda, graduation ceremony with the graduated features. Then we have the beta bloom, new alpha features, security, and finally what's changing in Gardener. Yeah, with this, let's directly hand over to Johannes and Toby, who were the responsibles for this version.
Okay, so hello also from my side. Tobias and I were the Kubernetes release responsibles for 1.34, so meaning we introduced Kubernetes 1.34 to Gardener and performed the changes in the core as well as in the extensions. So therefore, today we will talk about Kubernetes 1.34 of wind and will. So that's the name. It means, or it relates to the wind that propels us forward and our inner will that drives us. So it makes sense to have here a sailboat as a logo. Why there are bears, nobody knows. So if you find a good reason, let us know. So as Raphael already mentioned, we start with basically graduated features. We then go into beta features and alpha features, doing security deprecations removals shortly, and what has changed in Gardener. Not a lot, not to spoil too much. We have a fairly packed agenda, so if you have any kind of questions, feel free to reach out in the chat. We also noted down the Kubernetes enhancement proposals on the slide, so you can also directly read up or also later read up on the individual enhancement. While Tobias and I have been looking into the topics, we are no experts in any of these topics. So by all means, if you want to go really deep, you have to look into the Kubernetes enhancement proposals probably yourself. That being said, if we have time at the end, we may also have some time for questions, but like I said, please rather go into the chat. We will try to answer the questions during the presentations. So then let's start off with the graduated features. The most important topic or most prominent feature of the graduated features is dynamic resource allocation, DRA for short. Why is that relevant? So basically it provides APIs to make it easier to request or share resources among pods, make it more flexible compared to the existing device plugins. So as you may know, Kubernetes started fairly early with resource requests in the container spec within the pod spec, where you could simply add values. Now we nowadays live in a world where AI comes into all discussions, and that means you have to have also other resources next to memory and CPU, meaning GPU or tensor resources that you might want to share. And with device plugins, there was a capability to also do that via the existing resource sections of the pod spec, but DRA makes it a little bit more flexible. So DRA divides basically three personas: the device owner, the cluster admin, and the workload operator. The device owner is responsible for providing a DRA compatible driver. So for example, NVIDIA provides a driver for its own devices. The cluster admin is then responsible for installing the drivers, meaning a daemon set most likely, into the cluster and attaching the devices either virtually in cloud infrastructures or physically on a bare metal infrastructure. And the workload operator, last but not least, is the one that's actually running the workload. And then on each workload, so meaning on the pods or higher level resources, the workload operator needs to put corresponding claims in, so a resource claim or a resource claim template, which then via properties describes what kind of device this workload needs. So as you see, there are basically four custom resources being added: the device class, which can describe classes of devices. resource slice, which basically contains a couple of resources, and then the resource claim template and resource claim that can be referenced via workload resource. So if we look at that basically in a overview picture, how does it all relate to each other? On the lower level, we see basically kubelet running on each node. Kubelet has a plugin interface where the DRA driver can be hooked into. Then basically the kubelet calls the DRA driver via internal Unix domain sockets to adapt, for example, pod environment variables and so on. So the DRA driver can either put devices into the pod namespaces or also change, for example, environment variables. And it can also create the, or is most likely responsible for creating the cluster scoped resource slice, basically letting the whole cluster know which resources are available. So if a DRA driver detects that a resource or a corresponding device is available on a node, then it will create or register it in a resource slice. It is also possible, as I said, to create device classes, but they are rather optional. Then from the workload perspective, as mentioned, we have the workload resources like pods, and they can reference a resource claim. The resource claim then describes via properties what kind of resource it needs. The same is also possible with the resource claim template. The resource claim controller of the Kube controller manager takes basically the claim template is referenced, watches the pod resources, sees that the claim template is referenced, and then it creates a resource claim. Out of that. The Kube scheduler then, with the resource plugin, sees that when a pod with resource claims is to be scheduled, it checks basically by the resource slices where this pod can actually be scheduled. Now, this is where this might be obvious for some. It might not be obvious to everybody, and I think we think that the topic is rather important. Therefore, we want to also quickly go into a dynamic resource allocation demo, where Tobias will show us how this all fits together now in the real world.
Yeah, thank you very much. So, as Johannes said, we've prepared a small demo with an example driver, which is basically provided by Kubernetes. And we will start by installing it into our cluster. And after we have installed it, it automatically creates a device class. And device, so to say, and it's rather straightforward. So it's basically a class just saying that that GPUs of gpu.example.com belong to this driver. It also simulates resource slices or these GPUs to be available on the node. So now we see here, okay, we have like 8 different GPUs with some different attributes and so on, and index and UIDs and some memory capacity. If we now look on the node itself, on what it means in the first place, after we will see action moving, what happens at the end is that the device driver creates through the container device interface files that then get picked up by the container runtime interface to then inject env variables or devices, etc. into the containers, as Johannes also stated earlier. So right now we just see that there is one common file which gets injected into everything that uses this driver. So if we now look at the logs of the driver, we see nothing much. This is very debug output. So this is basically the function that gets called when a resource claim is being made and the device plugin needs to do something. Okay, so if we now have a pod that wants to use a GPU like this, so we have just a normal, very simple pod that just basically prints its env and does nothing. But it has this resource claim GPU here, which we create through this template. We just request one of these example GPUs. Okay, let's do that. So we apply this pod. And if we wait until it's ready, okay, now it's running. We can look into the resource claim that has been created. We see this resource from this resource claim template created a resource claim, and it is owned by this pod 0. And we see that Kubernetes has allocated this device GPU 6 to this pod. And if we now look into the pod to see what actually happened, we see in the env variables that this GPU device 6 somehow magically appeared here through env variables. Exactly. And if we now look into the node, we see that for this pod UID, we have a file, and okay. And in this file, it basically just states what the container should edit. And here we have these container edits, and see that these variables should be included in there. Normally, for example, the GPU, the NVIDIA driver does not do env edits, but it prepares the GPUs to be used, and then mounts them as a file to there. Exactly, and that's basically the main magic of it. So not going into all of the specific details and all of the objects, because there are many functionalities that can be used, but this is, as we said, like a bare minimum example on how this DRA works. Yeah, and with that, back to you, Johannes.
Okay, so like we said, DRA is very important, it's very prominent, but it's not completely done. So it will continue to develop. The base functionality is now available. It can be used for AI use cases, but there are other topics in beta and in alpha, so still in development with regards to dynamic resource allocations. We will not go into further details with regards to these topics. So there are, just to name a few examples, for example, the priorities alternatives in resource claims and resource claim templates essentially means that you can have different resource claims and basically order them. So for example, in plain words, I can say my resource wants the best NVIDIA GPUs, but if it can't get the best ones, then I can live with the second best ones. And now with prioritize alternatives, I can actually express this also in the Kubernetes API. And similarly, for example, admin access for secure resource monitoring means that an admin might have more privileges or might get more privileges to access, for example, monitoring of the devices, while an ordinary user has only limited access, so they cannot access the monitoring interface of the devices. So in that regard, there are a couple more dynamic resource allocation related caps that are part of this release, but from now on we will not go into further details. If you want to keep up to date with them, as you see here is the list, you can get more details. Now moving on to other released features. So we have delayed creation of job replacement pods. What does that mean? As you may know, I mean, usually pods are the workload entity, but there are higher level abstractions that are usually used, for example, deployments and daemon sets. But there is also something like a job. So cron jobs are somewhat obvious for recurring tasks, but you can also use job as something that should just run once, but should also complete successfully, meaning that the job controller will kick off this or replace a task if it failed. Now, previously, the job controller did that right away. So meaning if some job failed while it was still terminating, a new pod was created. This obviously could lead to simultaneously running pods, which is sometimes a problem. I mean, the noted problems are, for example, cluster autoscaler scale-ups, meaning if my pod requires a lot of resources while the other one is still terminating, then cluster autoscaler might think, okay, now I need a new node, scale up the cluster with my huge resource request, and then the other one terminates, and then it's basically useless. The other obvious thing is that not all frameworks, especially AI frameworks, can deal with the fact that there are two pods running basically for the same workload, for the same index. So there might be parallel access that might not be desired. So what is now possible? You have basically in the job spec, you have pod replacement policy, which you can simply say set to failed or terminating or failed. The previous behavior is terminating or failed. So that's also the default, but you can now also say, okay, I only want my pod replaced when it is really failed, so that it's when it's done executing. So next we have two features in the areas of volume management. One is here recovery from volume expansion failures. With Kubernetes, we live in a cloud world where basically everything is endless and you can scale forever. Well, not really. Usually everything has an end. And in terms of storage, this end is usually pretty near. But if you, for whatever reason, try to scale up a volume, whether you factor it or just are too optimistic what your provider can handle, you end up with a volume that tries to expand and it tries to expand and it tries to expand and will never expand because it will never basically be capable of expanding that much. The problem with that is that in previous APIs you could not really reduce the capacity. So the Kubernetes API does not allow to reduce capacity. Now with this new feature, if your volume is in a volume expansion failure mode, so basically if you try to expand it, but it has not successfully expanded, you can reduce the capacity. So you can do a smaller expansion under certain circumstances. So basically, I mean, the capacity could not be used. So, I mean, if you have, now in this example, if I had a volume before with 5 GB, I try to expand to 500 GB and that fails, then I can still say, okay, let's go to 10 GB. It's still larger, and I have not used more than 10 GB. So that's now possible. Again, depending on the infrastructure. The second volume-related topic is the volume class for volume modifications. On the infrastructure level, I/O quality of service parameters like I/O operations per second or throughputs are already possible. You could already match that with Kubernetes with a storage class interface. However, storage classes are immutable, so you cannot change that afterwards. And you might want to change for persistent volume. If your requirements change, you might want to increase the IOPS or the throughput or some other attributes, or you might reduce the corresponding parameters. Now with the volume attribute class, you can do that. You can have multiple volume attributes classes, and you can change the volume attribute class, for example, here in the persistent volume claim at any point in time, meaning that then your corresponding infrastructure resource will scale up or down according to the parameters. The parameters are obviously linked on the infrastructure. So next up, we have ordered namespace deletion. What does it mean and why is it relevant? Well, it's relevant because of security. In the past, the deletion of Kubernetes namespaces was basically everything in the namespace was deleted at any point in time in any random order. Why is that a problem? Well, we have pods. so actual workload running in the namespace. So the pods get deleted at some point in time, but also some entities that may be related to the security of the pod or security implications for the pod. Meaning, for example, network policies. If you have network policies restricting a pod and the network policy is deleted before the pod is deleted, that means that after the network policy is deleted, the pod may be able to reach endpoints that it should not be able to reach. So that was actually CVE as noted here, and it was addressed with ordered namespace relay deletion, which is now GA as of 1.34. So basically the solution is very simple: delete all the pods in the namespace in any order, wait for all the pods to be stopped and deleted, and then delete everything else. There are some issues still, but they are the same as before. If you have dependencies, so for example, owner references that lead to circular dependencies, then an operator needs to step in. That's the same behavior as before. So if basically you have a pod that has an owner reference to a network policy, then an operator needs to step in. This is actually now GA in 1.34, but it was also backported to earlier releases where it was not enabled by default. So staying within the security realm, we go for finer-grained authorization based on selectors. So now, this is basically mostly important for per node workloads. So for example, for daemon sets that only shall be able to access certain entities that are just for specific for the node. So now in subject access review, as you see on the right side, you can use field selector and label selectors. You can also use authorizer common expression language library and do the same with authorization, webhook, and match conditions. I think we already use that to quite some extent in Ghana, so that should be somewhat known.
All right. Next up is the structured authentication configuration that went to GA now, and some of you may already know it. But what actually changed is that instead of several authentication flags in the Kube API server, this is now being done through one config file, which is then referenced in the Kube API server as a flag. Old flags, like the flag approach, still works, but you cannot use both in mix. And yeah, the authentication configuration also allows to use several issuers instead of just one, as it was possible before. In general, for the basic use case, most of the fields just map one-to-one, so it was quite it's quite easy to migrate from A to B. But yeah, this then kind of looks like this. So you have on the left side the old approach, and on the right side the new approach, but with a file. And what is also possible, there's some further possibilities with this. So you can have more functionality with the authentication configuration that you did not have before. The Ghana clusters are already migrated to this approach since quite a time, I think. So all good from that side. Next up, this is also kind of regarded to that. This is about anonymous requests with fine-grained controls. So in the past, there was a Boolean flag in the Kube API server to allow or disallow anonymous requests to the API server. This is now also in the structured authentication we just talked about. And in addition to just having this Boolean field, you can also add explicit paths to for example, probe endpoints to probe the Kube API server for health without needing, so basically doing that anonymous. This is, as you can see, this is also in there. You have to turn on this Boolean flag to true to use these conditions, but then it is only allowed for these exact conditions and nothing else. So there's no globbing or or anything else like that. This is an exact match to these paths. Yeah. Exactly. There's now also what also went GA is the sleep action for container lifecycle hooks. So there's a new pre-stop action to Kubernetes natively allow sleeping for several seconds before the pod being killed. So this was possible before, but the image needed a sleep binary to actually handle it itself. What now happens is that when the pod is deleted, the endpoint controller already removes the pod from the service endpoint, so it does not get any more traffic. But the pod is not immediately killed, but the first like the X seconds will be waited before. Yeah, this then basically looks like this. So it's in the container lifecycle, pre-stop sleep. Exactly. What also went GA is the Linux node swap support. So for a long time, that was required for Linux nodes to disable swap. Otherwise, the kubelet won't start and would complain about that. Now it is possible that the kubelet starts even when swap is enabled, and workloads can use the swap. The swap limit per workload is calculated based on the available memory on the node container requests and limits. And until now, this is set in stone, by some magic formula. So if the pod or container would use more than the available swap, it then would also run OM. Yes. This is also a fun one. So the CRI now discovers the C group driver. So the kubelet had the possibility to specify whether the C group driver is C group FS or systemd. And nowadays it automatically detects what the CRI uses, and the kubelet then uses the same as setting two different values would run into a non-working kubelet. With that, it was deprecated in the kubelet to set this the C group driver manually, and container d 1.x, so every 1.x versions do not support this, and therefore will be non-functioning with Kubernetes 1.36, where this is eventually being moved. But for example, Garden Linux is already on container D 2.x for even the oldest supported release. So yeah. These are the honorable mentions that went GA, so we don't go into the specifics of that. Most of them are performance optimization or related to, for example, Windows nodes, which is not really that interesting in the scope of Garden. One nice mention is, I think, the API server tracing. So the kubelet and the API server now allow the tracing through open telemetry. Exactly. Now coming to features that went into beta. One of them is protected service account tokens for kubelet image credential providers. Very catchy topic. So a very catchy title. But in the end, this means that instead of image pull secrets, protected service account tokens can be used for image pulling. So for example, for private image registries, etc. So this can be configured in the credential provider config of the kubelet. But for that, in the end, the kubelet then calls a credential provider plugin to get this token in the end. So there needs to be the credential provider plugin installed on the node to be usable. So for example, I found it that it's possible for ECR that they provide such a plugin to be usable. Yeah, this then looks like this. So there's this credential provider config where you can basically specify for which images this should be happen, and then you can specify the token attributes, etc. So for which service account token audits, etc. So yeah, this is that. Another thing is the external service account token signing. So right now, the Kube API server gets a single signing key, which is then used for all the service account tokens. And what is now possible is to specify a service account signing endpoint, which has to be a Unix, a local Unix socket where gRPC service listens to and provides the keys, etc. Yeah, this is now beta, but I personally could not find any out-of-the-box implementations for any cloud KMS services. So these gRPC services, so these connectors basically would need to be built by oneself as of now to use this feature. Yeah, this is a nice operator usability or user usability feature in 1.33. The kubectl file was introduced, which is now beta, which allows setting custom aliases or command defaults regardless of which kubeconfig is used. So this is basically read by kubectl, and then you can set, for example, aliases for stuff that you need. This was possible before through the kubeconfig, but the community. So for me personally, I also did not even know this existed or used it. So this is now basically being done regardless of which kubeconfig is being used. So you don't need to have like custom bash aliases or scripts for that. So on the next slide, yeah, you have, for example, this example here, where you can have an alias, for example, for kgetn, which then translates to automatically put the output into JSON, so you get automatically JSON. So just as a small example, but this is quite powerful. Yeah.
Okay, then moving to a completely different topic, pod level resource requests and limits. As you may know, with Kubernetes, you can already specify resource requests and limits, and we have seen in the beginning, also with dynamic resource allocations, even another way to specify resource requests. Now, why is here a beta feature pod level resource requests on the list when we already have something like that? Well, currently or previously, the resource requests were simply on the container level. Now that works very nicely for ordinary pods that have just one container, but if you have multiple containers, it becomes a little bit more complex, especially if you have some sidecar containers or init containers that only do a little bit of work or only do work for some part of the time. It gets challenging to really use the resources or allocate the resources efficiently. So the result is mostly, or most of the time, that people over-allocate resources so that they play it safe for every container, and then the overall resource utilization is fairly bad. Now, pod level resource requests and limits tries to address this from on the pod level, meaning that now you can also specify resource requests and limits on the pod level that then relate to all of your containers. So, for example, if you look at the example on the right side for an IDE pod, where you have one container, the actual THEA IDE with certain resource limits, and then you have two sidecar containers, for example, a shell and some tooling that run all the time, but do not necessarily require the resources all the time. So now you can specify basically for the whole pod the overall limit, and now the sidecar containers can use those limits together whenever just one of them is running. So the overall pod, so all containers of the pod have a limit here of 1 GB of memory or 4 CPUs. But basically it can be that at one point in time just the shell container is using all of that or most of that. At some point in time the tools container, and then the IDE, it's limited itself to even less of that. So this is now in beta, and it's also supported by HPA. Another nice feature is mutating admission policies. Many of you may know we have in Kubernetes for a long period of time already mutating webhook configurations, meaning that you can basically manipulate any kind of changes of Kubernetes resources via webhook, which is heavily used by a lot of Kubernetes components. And in the whole ecosystem, it's very common. Well, what is the problem with webhooks? You have to actually run a webhook server. So you have to run a component that's actually being called by the API server. And if your component is down, you may run into troubles. For example, if the failure policy is to fail, then the actual mutations will not work. So meaning also you have to update your webhook server in a zero downtime fashion, because if it's down, then it has implications for the rest. Now it turns out that most of the mutations actually being done by mutating webhook configurations are fairly simple. And this whole trouble that I told you about the communication to the webhook server and running the webhook server, well, that's actually not necessary if you can specify the mutation in a simpler way. And that's what mutating admission policies is all about. You specify via a custom resource with common expression language the expression you want to change. Meaning if you just want to default certain values, if you just want to override something, but you can do that easily, but you can even do more complex things here with the common expression language. This is then directly executed in Kube API server, so you don't have to run any additional servers. You don't have to keep any server up to date. It's all directly in the API server, so you don't have latency concerns and other issues. This is now in beta. Then we have a completely different topic, tooling for declarative validation of Kubernetes native resources. It was already in beta in 1.33, but it was now enhanced in beta in 1.34. So what is this topic about? It's basically in Kubernetes, in the Kubernetes ecosystem, we have a lot of APIs that basically rely on Go implementations where you provide Go structs with some values, and then you have, for example, validation functions that check whether the values of these structs actually match to your expectation or match to boundary conditions. Previously, as also done in the Gardener ecosystem, we have basically written manual validation functions, so checking that minimum, maximum values, or generally some format is being fulfilled. Now with the declarative validation of Kubernetes native types, you can do that via comments in your Go source code, and then you get generated the validation functions automatically and do not have to maintain your manual code. So what is new, or just looking at an example to make it more obvious, on the right side you have, for example, a config struct with the min value and a max value, and the current value should always be between min and max, so there should be a minimum, a constraint that minimum should be min value, maximum should be max value, and that would be the validation. And in contrast, you would have, nowadays, you would have a validate function, which actually performs this in actual Go code. So what's new in 1.34? They have introduced ratcheting, which is a nice word, but basically this context, it just means all stored data is considered valid, meaning that if some previous validation has accepted some data, it will not be checked again. That means the generated validation will perform a difference check, so it performs a diff, and only the changed attributes are actually checked. Second thing is cross-field validation and then immutability. Cross-field validation is pretty clear, so you can validate against other fields. And immutability is basically, as noted below, it's maybe a little bit different than you would expect it to be. But here in the persistent volume claim spec, you can start with a empty volume name. You can set it once to a value. So for example, here the name PV123. But afterwards, you cannot change it or you cannot unbind the name to remove the name. That's basically the immutability. So there are different options that you can now use. I think in the Gardner team, there was already some ideas to use that also for input validation. So, and then going again, completely different area, in-place pod resize improvements. Again, this is also a feature that was already in beta in 1.33, but in 1.34 it was a little bit changed or extended, so that you can now also in place remove the decrease the memory that a pod request. So for example, here, if you have a front-end pod with a resource request of 10 gigabyte of memory, you can change it now to 2 gigabytes. For a CPU, that was already possible. That's also not a big problem. But for memory, the main issue is what would you do if the memory is actually used? So if the pod was already using 10 gigabyte, how would you then go to 2 gigabyte without running into out of memory? And actually, that's exactly what is not possible. But if your pod is not using the memory, so for example, if the front-end pod here in this example is using only 1 gigabyte, then you can do an in-place pod resize to 2 gigabytes without any issues. So the precondition or the boundary condition is basically if the memory is not being used, then you can also decrease memory in place. If the memory is being used, then you cannot. So there are also a couple of beta topics we did not look into further. Here noted here, if you want, for example, to know more about graceful node shutdown handling for Windows nodes, here you can look at CAP 4802. But most likely for most of you that's not relevant, so we will just move on. So, and we move on to the alpha features, so fresh off the press, what has changed, what is relevant with regards to alpha features. First important alpha feature is the support for KYAML, a Kubernetes dialect of YAML. You might wonder, we already have support for JSON, we have support for YAML. Why do we need something else? While some people like YAML really a lot, YAML also has some traps. Some people run in those traps all the time. Some people run in them fairly less often. But what are the traps overall? So one of the issues commonly referred to as the Norway bug is that basically YAML has special handling for some character sequences. So if you deal with country codes, so the two-letter abbreviations of the countries, then you might have run into the Norway bug. So if you have put an NO into your YAML file without any quotes, it does not turn out to be Norway, but it turns out to be actually a Boolean value false, because no is interpreted by any YAML parser as basically a Boolean value false, similar as yes is also Boolean value true. Quoting the string makes it obvious for YAML to use it as a string, but that's again for an unexperienced YAML enthusiast might not be that obvious. So, and there are a couple more things that are not so clear. I mean, due to the indentation in YAML, you might easily get something wrong. A file might look look correct, but it's not actually correct because the indentation is wrong, because things are not at the right indentation level. So that these are issues that KYAML tries to address. So basically, what does KYAML do? It always uses double quoting value strings. So basically, everything on the right-hand side is always quoted. The keys are never quoted unless they are not safe. So as with usual YAML, you don't need to quote them. But if you have something like NO, then you need to quote them to make sure it's actually a string or interpret it as a string. And then you have always curly braces for structs and maps, and always square brackets for lists. Now on the right side, you see an example of this, and you might wonder, well, that looks a lot like JSON, so why not just using JSON? Well, there are basically 3 points. What is different? Well, unlike JSON, this format still supports comments, which is nice. Unlike JSON, you can still have the comma of the on the last element of a list, for example. And unlike JSON, basically the keys are not always in quotes. Yeah, that's basically true, and you can make up your mind whether you want to use it or not. And with 1.34, it's now in alpha. YAML is not going away, and JSON is also not going away. So now you have simply a third option to look into if it's interesting for you. Second alpha feature here are pod certificates for MTLS authentication. MTLS is a recurring topic and relevant to a lot of advanced users, a lot of, or most of the time, service mesh implementations were used for that in the Kubernetes space. Now with 1.34 as an alpha feature, it's also possible within the pod spec to request projected pod certificates, and then the kubelet can or create the pod certificate request spec from the API server, so that each pod can get individual certificates and can use them for MTLS authentication.
Okay, next up there are the container restart rules, which basically means that instead of having restart policies per pod, this is now possible for each and every container as well. The background of this feature are basically, or the motivation behind it were mainly AI or machine learning workloads that are constructed of different pods that kind of also depend on each other, and where restarting or rescheduling a pod is expensive. So there might be a pod which has several containers, and one of them crashes, but it's just one of them, and it might be an exit code which can be retriable. So not the entire pod should be in a failed state, but just this one container should be restarted. So this currently only supports restarting on specific exit codes. Otherwise, there will be no restart. And more of that, more possibilities was also described in the CAP. But as of now, this is just this one feature or set of there. This then looks something like this. So you have one container that should never be restarted, except when the exit code is 42. Then it should be restarted. So this might be, I don't know, maybe some setup has not been done yet, or whatever, some network problems or something. This is to streamline these workloads there. Exactly. Another very frequently asked feature is now also in alpha, which is loading environment variables from a file that are created during runtime. So until now, it was only possible to put end variables or load end variables from config maps. So before the pod was started, but this is now possible to some extent during runtime of the pod. So there might be an init container that generates some env vars dynamically, so the values are dynamic, and then they have to write them into an empty dir of the pod, and then the main container can use a file key ref to automatically get this env var from this file. So now here, for example, we have an int container that just puts config var to hello into this slash data config.env, which then gets read by the main container through to this config.env path, and this is then set to this config underscore var, which then is then set in the env of the main container. Yeah. There are some as well honorable mentions. This time not so many. For the security deprecations removals, this is mainly some deprecations. So I talked about this already earlier. So the two deprecations are related to the automatic cgroup driver detection of the kubelet. So the manual cgroup driver configuration and container d1.x support is deprecated. And for the traffic distribution, there was prefer close. This is now deprecated. And as a replacement, there's prefer same zone, which has the same meaning and the same functionality as prefer close. But in addition to that, there's also now prefer same zone. In terms of security, there's the one CVE that Johannes also mentioned earlier about ordered namespace deletion, or about the pods basically able to outlive the network policies, for example. This is one CVE that is addressed through this release. Exactly. Now to what's changed in Gardener. As Johannes already spoiled a bit, it's not that much. So the support for Kubernetes 1.34 is available in Gardener Core since 1.132, and the provider extensions, Ali Cloud, AWS, Azure, GCP, and OpenStack will be released soon. So most of them are already released. I think only AWS and OpenStack are missing at this point, but will be there soon. So you don't need to wait too long for that. And with that, we come to an end. Thank you very much for listening. And if you have any questions, leave us in the chat. And as Johannes mentioned, may be possible that we don't know all of the answers to all of the specifics of that. Thank you very much.
Awesome. Thanks for presenting this. This was great. So theoretically, we would have 3 minutes left, but you prefer to take questions asynchronously read.
If there is another question, just shoot. That's
okay. Anybody?
I have a quick question. Are you aware of any downsides of using mutating admission policies compared to webhooks?
If you've looked at the API, it's a little bit challenging to get into it. once you have understood it, you can use it. And I think you cannot do too complex things. So I think you're limited also in terms of execution time, how much you can do. But I think for simple changes, mutating admission should always be the preferred way to do, because you get around all these the potential network issues, the potential lifecycle issues with your server. So I think it's a clear win from my point of view, but it is not completely straightforward to do. If you, for example, if you just want to add one to a field, that's not just +1. I think it's the CR will look a little bit more complicated. That's the only thing.
Okay, thank you.
Good. Then I guess we close it for today. Thanks everybody for joining. Next week we go back to our regular bi-weekly cycle and start with the first release that is about to be released end of this week. So until then, have a good time and see you soon. Bye-bye.
See you soon. Bye-bye.
See you. Bye.
Bye bye.
Thank you.